Hello, we're going to thoroughly discuss the process of testing the normality assumption that underpins our time series variables. We'll be using the Finance ResearchGate website for this demonstration. But first, it's crucial that we establish the theoretical foundation. Our presentation today will focus on two distinct statistical assessments, specifically the Jarque-Bera test and the well-known Shapiro-Wilk test. The initial test we'll examine, known as the Jarque-Bera test, is designed to evaluate the normality of a dataset by carefully considering its sample skewness and its kurtosis. So these are the two primary variables we're going to be looking at here. Now, when it comes to the Shapiro-Wilk test, it's a bit different. We primarily rely on the ordered sample data and, more importantly, the overall shape or distribution of those observed values. So let's begin our discussion by focusing on the first of these, which is known as the Jarque-Bera test. We need to identify and then calculate quite a number of different variables. Our very first crucial step involves determining the deviation from the central mean value, and only then, subsequently, can we accurately compute the overall variance for our data. After we've calculated the deviation, we're then able to create a variety of metrics. Considering the first one, if we take those values and square them, and then we average the resulting square deviation, we will arrive at what's known as the sample variance. However, if we take the deviation and then raise that specific value to the power of 3 and subsequently scale this result by the overall variance, we will then be able to calculate the sample skewness. So when we raise that value to the power of 3, it's important to understand that we are not actually changing the fundamental sign of that specific deviation. It's crucial to remember that in any given statistical distribution, any data point that lies above the mean will inherently exhibit a positive deviation, whereas any point falling below the mean will always show a negative deviation. When considering any series of data, we will always find both positive and negative deviations. When we raise a value to the power of 3, we will maintain the original sign of the deviation, unlike what happens when squaring it or raising it to the power of 4. So, when we raise that particular value to the power of 3, it will inherently maintain its original sign. What this calculation is truly measuring for us is the overall extent of our positive deviation in comparison to the negative deviation. If, for example, we observe a greater number of positive deviations compared to the negative deviations, this indicates the presence of skewness. Specifically, in this situation, it is skewed to the right. Or if you have more negative deviations exceeding positive ones in magnitude, it means we have negative skewness. A normal distribution should exhibit zero skewness, meaning that there is a perfect balance between the positive and the negative sides, or more precisely, a balance between the right tail, which extends up above the central mean value, and the left tail, which falls below that mean value. So, it's possible to have a negative value, and in this specific instance, we're seeing either left skewness or positive right skewness. In either of these situations, we clearly have a deviation from the normal distribution's central value, which is, of course, 0. For the other measurement, kurtosis, we raise the deviation to the power of 4 and we scale it by the variance even squared. So in this context, raising a value to the 4th power effectively eliminates the negative sign of any deviation, ensuring that all deviations would invariably become positive. However, because we are raising that specific term to the power of 4, this inherently gives a much higher weight to the extreme values. Consequently, if we observe fat tails in the distribution, that will inevitably lead to a significantly higher value in the numerator, and therefore a much higher overall value for the kurtosis. The normal distribution possesses a specific value for its kurtosis, and that standard value is precisely 3. When we talk about fat tails, we're referring to a situation where extreme observations are much more likely to occur than what the standard distribution would predict. This implies a higher probability for outliers. This characteristic is technically known as leptokurtosis. However, if we observe tails that are quite thin, even thinner than what a standard normal distribution would typically dictate, then we are dealing with a condition known as platykurtosis. So, for our current analysis, we're going to introduce the concept of skewness, and in addition to that, we'll also examine the kurtosis. Then, as part of this process, we'll be squaring each individual term. Now, what we're describing here is specifically known as the excess kurtosis, which is essentially the excess amount, or more precisely, the difference that exists between its calculated value and the number 3. We calculate its square, and we also calculate the square of the measure of skewness. In this particular scenario, we then have a chi-squared distribution that we can use to compare our x value. It's important that this value is greater than 0 since we are performing a squaring operation. My loss will be squared. So, in our calculations, we always end up with a positive value. The expected normal value based on a standard normal distribution is precisely 0. Therefore, if our observed value is greater than 0, it indicates that we have a significant potential to reject the null hypothesis, which assumes a normal distribution. But how can we effectively compare our observed value to the predetermined benchmark value? To achieve this comparison, we specifically rely upon a chi-squared distribution. This particular distribution is what we observe when operating under the null hypothesis, which posits that the underlying data distribution is in fact normal. If the Jarque-Bera value is quite large, it indicates that this particular value would be positioned at a very extreme level within the context of this statistical distribution, assuming, of course, the normal hypothesis holds true. In this specific scenario, the probability of us accepting that the observed JB value is truly normal, given the underlying characteristics of this particular statistical distribution, would be extremely small. Therefore, if the p-value happens to be less than 5%, or indeed if it's observed to be quite small in general, this indicates that we are able to confidently reject the null hypothesis, which states that the JB statistic we've calculated belongs to that specific distribution. We reject that premise because it's based on an extreme value, an outlier, representing just one end of the entire data distribution. However, if the p-value turns out to be greater than the typical 5% threshold, or is simply quite large, then we do not have sufficient evidence to reject the assumption of normality. So in this particular instance, we accept that the specific Jarque-Bera value that we have obtained through our calculations actually belongs to this particular distribution under the assumption of the null hypothesis, which states that the underlying distribution is indeed normal. For the other statistical test known as the Shapiro-Wilk test, the fundamental approach, the method is different, but the purpose is still the same. We are just measuring how closely the observed distribution resembles the standard normal distribution. Again, the normal distribution is characterized as a bell-shaped curve. It assigns minimal weight to the extreme values, while conversely it allocates greater importance to the central numbers, specifically where the mean and the median are equivalent. So for our example here, let's just assume we're dealing with a certain number of values, specifically, let's say, only 6. Our initial step in this process is to calculate the average of all these specific values, and we have already obtained that resulting number. Following that, we then proceed to rank these values, arranging them in order from the smallest to the very largest. You can see them presented here, clearly ordered from the smallest up to the largest. And then we generate the alpha, which is essentially the weight pattern that we would acquire if we are operating under the assumption of a typical normal distribution. So, the values that we obtain in this instance are solely determined by the sample size. Given this, we only have 6 observations, so we then calculate the alpha. These values are not generated or affected by the specific numerical values, the actual data points of the time series variable that we currently have. So, that is going to be the weight according to the normal distribution. Then we take that specific weight and multiply it by the corresponding values. So this particular one represents the lowest value. We then proceed to multiply it by the smallest possible value. Therefore, it's absolutely crucial that we meticulously maintain the exact order or rank of these specific values, ensuring we can multiply them with complete accuracy. That will be multiplied by the second largest value, then the third, the fourth one here, and so on. Once we have successfully multiplied all of the individual values together, we then proceed to square that resulting product, and subsequently we compare this squared result against the overall variance. Therefore, it becomes necessary to scale this entire quantity by incorporating the variance. Consequently, when we proceed to divide the numerator of our expression, once we have divided the value by the variance, the numerical outcome that we then obtain, that particular result, should consistently be less than or precisely equal to 1. If it's exactly 1, this indicates that we possess a perfectly normal distribution. If the value falls below 1, then we are clearly deviating from what would be considered a normal distribution. So let's direct our attention back here to the weights. Just imagine, for example, what would happen if we were to change that to a completely different number. Let's consider a situation where we have a value of 0.2. What kind of impact or change would we then observe on the Shapiro-Wilk test statistic or its corresponding W ratio? Here, that value will be multiplied by the same number because these numbers are designed to tell you exactly what the weights or the weight pattern will look like under the normal distribution. So we are going to multiply that same number, which is now considerably higher than it was before. We will change its value to 0.2 using this method. The fact that it didn't rise to properly reflect its increased worth, and concurrently, this particular outcome is bound to generate a noticeable surge, quite possibly a truly significant escalation in the statistical variance. It's important to keep in mind that our calculations are being compared directly to the variance. So if we present an extreme data point or value, this will inevitably inflate the variance, and consequently the overall W value will then significantly decrease. This is precisely why, if a value is below 1, it indicates a clear deviation from the normal distribution.
Donc, if we observe the left tail to be negative and the right tail to be positive in a manner that closely resembles the behavior of a normal sample tail, then the overall weighted sum will consequently increase.
When the distribution's tails are either too heavy, too light, or perhaps asymmetric, the overall alignment weakens, and the statistical validity of our findings will significantly diminish. Now, let's proceed to apply these analytical approaches using the Finance ResearchGate website. I will begin by selecting a specific time series, and then we will proceed to analyze the data on a monthly basis. We should begin our examination from the year 2000, extending through to 2010.
And apply.
Let's go ahead and select the variable to be the monthly rate of return. Then our next step will be to construct this analysis for a very specific economic sector. For our purposes, we have decided to pinpoint the industrial sector. Consequently, what we are aiming to calculate is the industrial sector's monthly stock return. So, within this particular sector, we have quite a number of firms. We will then proceed to calculate the average monthly return, and subsequently, we will generate a single number for every month that represents this specific sector. We are in the process of creating a time series variable. Apply. These are the companies operating within that specific industry, detailing its makeup. And if we look down, we can clearly see the numbers right here. And now, as we proceed further down this document, we'll encounter the basic, straightforward summary statistics. The specific portion that holds the most significance for our current analysis and particular case is clearly represented by these distinct numerical values. First, the Jarque test indicates a value that is greater than 0, and it is also considered statistically significant. This is because the p-value is extremely low, approaching 0. This means quite simply that we must reject the assumption of a normal distribution. In addition, the Shapiro-Wilk ratio itself was observed to be less than 1 and, importantly, statistically significant. This also implies that the findings from this second test similarly lead us to reject the idea that our data follows a normal distribution. This means that our data distribution is not following a normal pattern. Let's now look at the visual inspection presented below. Upon conducting a visual inspection, we can clearly observe the histogram shape and the frequency distribution of our raw data values, or alternatively, the values that have been grouped into bins. If you look closely at the center here, you'll see that we appear to have what looks like a normal distribution. And if this indeed represents a true normal distribution, then what we would expect to see is a characteristic bell-shaped curve, just like the one shown here. This is not actually what we observe in reality, because primarily we are seeing instances of extremely high positive values, and these values have a much greater probability of occurring than what would typically be predicted by the standard normal distribution. Even if you were to significantly increase the total number of bins available, it still wouldn't alter the fundamental conclusion we've reached. So, you will ultimately have either finer or more granular bins. However, despite this, it remains evident that certain extreme observations are still registering notably high frequency values. The frequency, in essence, is just the count of how many times a specific range of values appears within your data sample. Below here, we have the density function displayed. Here, we can see the ideal representation of what a normal distribution should look like. In contrast, this one right here represents the actual observed distribution. This comparison allows us to calculate the precise percentage of all the data values that fall within a specific defined range. As an illustration, let's go ahead and switch this display to a full screen view right now. And then following that, we were able to observe and analyze the specific numerical values displayed in this section. As a clear illustration, for example, the particular density measurement that we find positioned very close to the 0 point on our scale registers at exactly 6.7. So, this means that for each individual unit, we're looking at a density value of 6.7. For example, if you were to multiply that specific number by just one person, it's because we don't have a full 100% here. Instead, it represents a 1% range of values. So, if we were to determine a 1% range of values that fall below this line, like this point and this other point, then approximately 6.7% of the entire distribution would be contained within this specific range. And it's important to notice that the mass of this distribution is concentrated right in the middle. However, we are observing some clear deviations from normality appearing on the tests. For example, in this specific region, we are currently observing a quite significant density of distribution, whereas the normal distribution would suggest we should have almost none present here. So, this will also support the conclusion that the deviation from normality happens on the positive tests as well as on the negative tests. You need to return to the previous state or location, and from there, we can effortlessly download the relevant information by saving it securely, should we require a more in-depth and comprehensive analysis later on.
So the overarching conclusion we've drawn is that our data distribution is definitively not normal, primarily because it's driven by the presence of extreme positive values, which exert a much stronger influence than the corresponding negative values.
So this is our conclusion. Does that mean we've found an error in the variable? No, not necessarily. That could be the economic situation or conditions.
The underlying economic reasoning that explains the nature of the variable.
For example, consider our analysis of monthly stock returns. We often find that in certain periods, the market might experience a significant downturn, perhaps even a crash. However, in other periods, we could observe a very rapid recovery, which then leads to a sudden and substantial increase in positive returns.
So it could simply be a normal economic meaning behind it and not necessarily indicating an error in the process of estimating or constructing the variable. So, is it really that important to have a normal distribution? We generally prefer to have a normal distribution before we proceed with further analysis, especially for things like regression. The primary reason for this is that the p-value, which is crucial in statistical tests, fundamentally assumes that our data follows a normal distribution. If not, then the calculated p-value, for example, the statistical significance of the observed relationship between different time series will be inflated. So, in this particular instance, we'll need to rely on a different type of distribution rather than the typical normal distribution. That concludes our session for today. Thank you all very much for listening.